Okay, so the very first lecture we will start with something called metric space. So remember that suppose we have a real line, okay, it is minus infinity, this is plus infinity. If we take any two particular points r1 and r2, we can measure the distance in between these two points, right? That is again mod of r2 minus r1. You can measure this particular distance. What is the distance between this? In fact, if we have any in r2, we can also measure the distance, or no, I should not use the fact called measure. I should use a determine. Okay. In fact, I can talk about the distance between any two distinct points. Okay. So if we, let's say it is x1, x2, y1, y2. So this particular distance is nothing but square root of x1 minus y1 square plus x2 minus y2 square. There is a distance. Now our target is to see that whether is there any arbitrary or a more general setup, that is, we will see that it will be denoted as x comma d, where suppose we have any matrix, we have any set x which is not any r or anything else. What is the most general form that one can induce on this x, let's say it is d, such that with the help of d we have the notion of distance between any two particular points. So that is will be denoted as something called metric. So first let us give the definition. So the definition is, suppose x is not equal to phi, it should be a non-empty set. Then we define a function d which is from x cross x to r, and such that for all d of x comma y is larger or equal to 0, it is always non-negative. So it is enough to take r larger or equal to 0. Instead of entire real line, if we restrict ourselves into non-zero real numbers, non-negative real numbers, then we are good enough. Okay, so if we have any function like this such that so when we call that this particular function is said to be a metric on x, if the following are satisfied. So what are the properties? Number one, d of x comma y is always larger or equal to 0, and d of x comma y is 0 if and only if x equal to y, otherwise no. So that means there are two options: d of x comma y either will be strictly larger than 0 or will be equal to 0. Strictly larger than 0 is if x is not equal to y, and e is equal to 0 will be when x is equal to y. Okay, number one. Number two, for any x comma y belongs to let's say x cross x, we have d of x comma y is same as d of y comma x. Means it doesn't make sense that whether you are going from x to y or you are going from y to x, whatever path you choose from x to y to x, you have to traverse same amount of distance. Okay. And number three is that suppose x comma y comma z, this belongs to x be any particular, okay, now let's say double. Yeah, so whenever we take any three elements from capital X, then we have d of x comma y is less or equal to d of y comma z plus d of z comma x. The second property is said to be the symmetric one. Symmetric property. And the third one is said to be triangle inequality. So what is actually what does this last condition implies? Last condition is implying that suppose we have here x1 comma y1, sorry, suppose we have x comma y, here is my x, here is my z, and here is another point, let's say y. So this means that you have two options to traverse from x to z. So either you go directly from x to y via this line, or you may go first from x to y, and from there you may go to y to z. Okay, so that means you have to take this particular traversing path, otherwise you have this one. So this third condition says that, and it is very very clear from the pictorial representation, that if you go from x to z, the amount of distance what you have to traverse from x to z is very very less than this amount, the sum of these two distances. Like you are traversing from x to y and then traversing y to z, the sum of the distance is very large than this traversing distance from x to z. Okay, so that particular thing is basically implying in this third condition. So that's why it is said to be the triangular inequality. Okay, like the sum of these two sides is larger equal to sum of this side, third order. Okay, so then we say that x comma d is a metric space. Okay, so metric space means once you have a metric space, you have to quickly keep in mind that you have a very fantastic metric defined on that. Now the question may appear, that first of all, is the metric unique, and secondly, do every set has a metric on it? So let us begin with to answer with the second question, that suppose we have a x is a non-empty set. Okay, and I am defining the metric d on x cross x to r larger equal to 0, such that d of x comma y, it is either 1 or 0. So when it is 1, when x is not equal to y, and when it is 0, when x equal to y. Okay, so then this will be a metric, and this is said to be a discrete metric. So whenever I have a non-empty set, I can define a discrete metric on it. Okay, so as an example, we will see that suppose we have x equal to r. So r has, we can define there are infinitely many metric on it. Okay, All right. So just let us keep it for a while. Okay. Now let us give some example of very beautiful matrix. So as an example, as usual, suppose we have Rn where n is larger or equal to 1. There we can define a metric D on Rn cross Rn to R is larger or equal to 0, such that D of x1 comma xn comma y1 to yn from here to square root of sum over I equals 1 to n mod of xi minus yi square. Okay. Now similarly, for any prime p, you may define d of p, which is from Rn cross Rn to R larger or equal to 0, such that dp of x1 up to xn comma y1 up to yn is equals sum over I equals 1 to n modulus of xi minus yi of p whole to the power 1 by p. So this is basically metric induced by p norm, and this metric is said to be Euclidean metric. And when the classification is concerned, you can also say two norm metric, because here just we have p is equals 2, then it completely boils down in this particular way. Okay. All right. Also, we can define another metric d of, let's say it is d1 is mapping from Rn cross Rn to 0, such that d1 of x1 up to xn comma y1 up to yn is equals sum over I equals 1 to n mod of xi minus yi. So this is said to be rectilinear metric or we say it taxicab metric. Okay, so all these are example of metric space. In fact, if we have any non-linear space, suppose X be a norm linear space with respect to the norm this, then we define d of x1 up to xn comma, or let's say x comma y itself, norm of x minus y. Okay, so this is how one can define the map. So this is said to be non-linear metric. So it is metric induced by the non-linear space. Or the norm, the norm. Now there is something called, let's have some basic definition that you must be aware that, okay, suppose we have a set X be a metric space, and A is subset of X, then A is said to be bounded if there exists m belongs to natural number, m belongs to real number, always of course should be strictly larger than 0, such that for any x comma y belongs to A, we have d of x comma y strictly less or equals to m. So that means m is basically the bounded of this map. This metric map. Okay, and the diameter of this map is defined basically supremum of all d of x comma y such that x comma y belongs to A. This is how we define the diameter of the set A. Now based on the boundary, so why I have induced this particular notion, based on the boundary we can define something called a standard bounded metric. So standard bounded metric means, suppose we have X be metric space, x comma d is a metric space, then another metric we can define d dash from x cross x r strictly larger equal to 0, such that d dash of x comma y is equal to minimum of 1 comma d of x comma y. So this d dash is said to be standard bounded metric. Okay. Now there is something called metric subspace. There is like a vector space, that if you have any vector space, then any subspace which is a vector space by itself and with respect to same addition and scalar multiplication, then it is said to be a vector subspace. In the same way, suppose you have X be a metric space and A is subset of X. Now you see that in case of vector space, you had to have the, closeness property, right? That if you take any particular element from the field and underlying field, and any another element from the vector subspace or subset, the scalar multiplication should be inside the subset itself. But here you don't have this closeness property, so it is enough. But you can easily check that once you have any A subset of X, also it is non-empty, then D of A comma B is same as D of B comma A, D of A comma B plus D of B comma C is larger or equal to D of A comma C, and D of A comma B is 0 if and only if A equal to B, otherwise strictly larger than 0. Because all the elements we can boils down this entire thing in, once you take these elements from A, B, C from capital X, you look at those elements in X. Okay, so just in terms of elements of the mother matrix space, so then all the properties will easily satisfied. So that means if you have any subset of this matrix space, subset of this underlying set, then if you restrict your D at A cross A, this is also a metric on A itself. So A, let us call it as DA. So A comma DA, this is a metric space. In fact, it is subspace. Okay, so as an example, suppose R comma D Euclidean metric, okay. Suppose closed 0 closed 1, this is subset of R. Then of course closed 0 closed 1 comma D instead closed 0 closed 1 cross with closed 0 closed 1, this is subspace of R comma D. As well as if you take set of rationals, then Q comma D is also subspace. Okay, now there's a non-example. That non-example means the motivation is the following, that suppose X comma D is a metric space. So Y is subset of X, suppose, and of course it is non-empty. Suppose you have another metric space Y comma D1, this is a metric. So metric space with respect to certain metric D1. D1 need not be D itself. Then is it every time true that D1 is induced from D? Okay, that's the question. So the answer is no. So as an counter example, let us consider a circle S1 which is the form cos t comma sin t, where this belongs to R2 such that t is in between 0 to 2 pi. Okay, So that means we are taking this way. This is my x-axis, this is my y-axis, and so suppose it is my circle. Let us keep it some more above. Yeah. So here is my circle. Now the question says that suppose now this is my subspace. So of course S1 is subset of R2. So if S1 is subset of R2, we define a metric S1 in the following way, that suppose D1 is defined from S1 cross S1 R strictly larger than 0, such that D1 of, so any two particular point, let's say sine theta comma, sorry, let's say cos theta comma sine theta, and cos phi comma sine phi, and okay, and so yeah, okay, sorry, this one is fine. So D1 is defined that it is minimum of modulus of theta minus phi or 2 pi minus modulus of theta minus phi. Okay, this is how one can define the map D1. So that means suppose we have any 2 point, let's say let us consider that here you have 1 point here and another one here. So let's say here is my point P or P1, here is my point P2. So this is my theta at the anti-clockwise direction, this is my phi at the anti-clockwise direction. Okay, so this P1 has coordinate cos theta comma sin theta, and P2 has coordinate cos phi comma sin phi. Okay, so if we have this map, so basically this takes either, so basically this map, what does this D1 means, either this one, then either in or this one, whatever. Okay, if this one and this one, whatever is less than there. In fact, if we consider, let's say here if we have any map, so then this is larger same as this, so whatever is minimum in between this and this, that will be the value of the at the D1. Okay, so now there are several checks that this is a metric. In fact, you can check the D of p1 p comma p is always 0, because if we have p1, let's say here, and p1 and p2 are same, and that means mod of theta minus theta is minus p is 0 basically, so that will be 0 only itself. So now the problem will be challenging part will be the triangle inequality. So triangle inequality means, suppose we have another metric like this, and I mean let's say another point in between p1 and p2. We have another point, let's say it is p3. Assume that this is xi, so it is cos of xi comma sine of xi. So then d of p1 p2 is now you see that d of p1 p2 is nothing but, so mod of theta minus phi, and from the picture represented it is phi minus of theta. Okay, so that means it is less or equal to 2 pi minus phi minus theta. Similarly, what is d of p1 p3? D of p1 p3 is just this one, that is phi minus xi. So d of p1 p3 it is phi minus xi, and it is mod, take it is mod. Keep the mod one, and d of p2 p3 it is mod of oh sorry, not theta, not phi, it should be theta. Yeah, p1 and p3, so it should be theta, and p2 p3 should be phi minus xi. So that means now it is enough. Now it is trivial that d of p1 p2 is less or equals d of p1 p3 plus d of p2 p3. But suppose we have some different case, like instead of p3 here, let us consider that p3 is something like this. So now this is my xi. So then, so in this case, what should be d of, so yeah, let us take, yeah, so replace it here. So what is d of p1 p3? This is 2 pi minus modulus of theta minus phi. Okay, and what is d of p2 comma p3? It is mod of no sorry, it is theta minus xi. It is mod of xi minus phi. So from this picture representation, it is clear that xi is larger than phi, so you can omit the brackets. Just that's why it will be just xi minus theta, and it is xi minus phi. So if we just add them up, we should get that d of p1 p2 equal to 2 pi minus phi minus theta. So it is basically 2 pi minus modulus of theta minus phi, because phi is larger than theta in this case. So that's why, based on the cases what we have, we can clearly say that d of p1 p2, and of course it is less or equal to this, right? Because it is nothing but mod of theta minus phi. So as per the definition of the metric that you have chosen on S1 here, once you choose the value of metric to be theta mod of theta minus phi, that means less or equal to this itself. So that means the metric that we have chosen d1 is a function we have chosen, is basically a metric on S1. So that means this S1 comma d1 is a metric, but not induced by the Euclidean metric. Why? Because once you consider the Euclidean distance between P1 and P2, you are basically considering this distance, right? Let me make it colorful. You are considering this basically this particular distance, right? Whereas the matrix D1 is nothing but this particular arc. You see that you are considering this one only, so this particular arc only. So the distances are completely different. The matrix value of interest is completely different. So that's why it is not we have the matrix we can define on metric, what you can define on S1 in this way is not induced by the Euclidean metric. So this is the thing. All right, but so that is an example that one the metric is not unique. Like on S1 you have two choices, one is this one, another one is a normal Euclidean metric. So that's why in a metric space a particular set can have different metric space structure with respect to different metric. Okay, now we have already introduced the notion of norm space. So what about the norm space? Suppose K be a field and maybe field we can say set of real numbers or set of complex numbers, whatever be comfortable we are. So then we define the norm on let's say V is a vector space over K. We define norm is a mapping from V to R. Of course it is larger or equal to 0, says that norm of V is always larger than 0 for all small v belongs to capital V, and norm v is equal to 0 if and only if v is equal to 0. First one. Next is that norm of alpha times v equal to mod of alpha times norm of v for any alpha belongs to k, and norm of v1 plus v2 is less or equal to norm v1 plus norm v2. So then v with respect to this particular function is said to be a non-linear space. So as an example, suppose we have R, if a metric space is Rn, is a vector space over R, there are usual norm, that is a norm of is equal to square root of xn square, or let's say we have it is a sum over mod of xi equals 1 to n, or any p norm with respect to x1 of xn is equal to sum over I equals 1 to n xi to the power p whole to the power 1 by p. Or something called maximum norm also can be defined. Maximum, that is equal to max of mod xi equals 1 to n. So all these are the metrics on Rn. Okay. So also let us take some more special example. So as an example, we can consider that suppose let's say R is a field, and we consider fx belongs to set of continuous functions from R to R. In fact, we can take any nonlinear space, any non-empty nonlinear space we are defining on R. So in that case, what norm we can define on F is basically sup norm mod of fx says that sup norm scheme of x says that x belongs to R. So it is sup norm. So this is how one can define the norm space in this way, and based on the norm we can define a metric in the usual way, that suppose X be a non-linear space or non-vector space, whatever. So then any distance between any two particular function, that is d of x comma y, is norm of x minus y. This is how one can define the norm, metric space with respect to the norm. So it is a norm-induced metric. It is said to be norm-induced metric. Okay. All right. So this is enough for today. We have just give a brief introduction of the metric spaces, and I expect that you will follow all these particular books that we have mentioned in this way, in this list up, and brush up this concept that we have discussed today. In the next lecture, we will define or study the topological properties of metric spaces. Okay, like the balls, open balls, closed sets, etc. All right. So, thank you very much for today.